Well, good morning, everyone. Glad to see that we have some folks that are having a look at the stream this morning. We've moved on into Chapter 13 material, so that's a little bit new. That's dealing with electricity and stuff like that. So quite a bit of a departure from what we have talked about, but it's still, I think, interesting and useful to folks. So also, if you could give me a little bit of a thumbs up or something like that in the chat, say hello or something like that, so that we, so I know who's here and watching and might have questions. Feel free to do that, please, so that we can have a little bit of interaction here, so that I know what's, like I said, so I know who's here and present and thinking about stuff. So, and also, I'm gonna, like I have been lately, give a little bit of a, hey, good morning, Michael and Avery, good to see you. So what I plan to do here is talk a little bit about some of the basics of electricity. Good morning, Josiah. Some of the basics of electricity and maybe some of the stuff that we would normally have covered, but because our semester was a little bit compressed, we didn't get to talk about it. We would have talked about Chapter 12 first, which is the basics of electric charge and electric force, and then moved into Chapter 13, which is practical applications and circuits. I decided to skip Chapter 12 and move on into circuits because I think circuits is something that's a little bit more practical and interesting, and I tried to sort of compress the basic stuff out of Chapter 12 that we were going to use into part of that first lecture that I concocted for Monday. So I'm going to flesh out a little bit of what electric charge is and what it does and how it operates to start with here, but don't let that stop you from asking any questions on any of the lecture material that you've seen already or any of the homework problems that we have. Just pop those questions immediately in the chat. If you're thinking about them, just ask them. Don't wait for me to stop or get going, because remember, the lag here means that I won't see your questions for a little bit anyway, so that's why I'm going to give that little bit of a fleshing out of Chapter 12 material first to give you a chance to get your questions posted into the chat here. I didn't see any questions on the discussion boards, but I'll have another look here while I go. But let's dive right into that Chapter 12 style material that we would have covered that we didn't get a chance to do here first. So this will give you a little bit more background on how electric charge works, so that maybe you can think a little bit more clearly about this material in Chapter 13 that has to do with circuits and the flow of charge. So the basic idea is that electric charge comes in two different varieties. There's positive charge and negative charge. And the reason why folks came up with that is because they noticed that different styles of charge, static charging end up happening. And you can notice this. You can say, well, I could take, there's two different types of charge. Some of them repel, some of them attract. And how do we figure out how that works? Well, basically, the upshot of all of that investigation in the 1700s was that we defined positive and negative charges, where usually the symbol that we use to represent how much charge there is on something is Q. So I'm going to say, let's say we have a positive charge right here. So I'm going to put an explicit positive sign in front of that. So I've got some amount of positive charge there, Q, and then I've got another charge here, let's say that it's negative. Okay? It turns out that opposite charges attract one another, like this, and the strength of the attraction that the two charges feel towards one another depend on how much charge there is and how far apart the charges are. You will notice that this actually looks a heck of a lot like Newton's rule about gravity, where the attraction that masses feel towards one another depend on the mass that's involved, and also the separation between the centers of the two masses. It's exactly like that for charge, except it's not mass that matters for determining how much attraction there is. It's the amount of electric charge. And the electric charge that you have, I mean, you experience this all the time. I mean, if you comb your hair and, with a vinyl comb or something like that, a plastic comb or something on that, like that, then in the wintertime, you'll get static electricity in your hair, and that your hairs will repel because, that's why they stick up. It's because when you comb your hair, the same amount of charge ends up on all of your hairs, and they repel one another, and where normally they'd be happy laying right down next to one another or something like that, like charges repel, as we'll talk about in a little bit, and therefore they want to be far apart, and it pushes the hairs apart and makes them stand up. So, and you know that if you comb your hair more, you can actually get it more staticky, which basically means more charge is ending up on your hair. And what's happening there is the stripping off of electrons in the atoms in your hair. So, but basically, let's go back to the idea of the attraction of these two opposite charges. So I have positive charge here, negative charge here. They attract one another. So this positive charge would feel a force to the right. This negative charge here would feel a force to the left towards the positive charge. And the more charge that was involved, the stronger that attraction would be. But the distance between the charges also matters. The further apart they get separated, the weaker the force gets, just like gravity. It goes just like gravity also in that it falls off like the inverse square. So the further apart they get, if I double the distance between these two charges, for instance, the force between them would go down by a factor of 4. It would be 4 times smaller. So if it was 1 Newton of force, it would go down to a quarter Newton of force. And if you separated it even further, like 3 times further away, it'd be 1/9 the force, and so on and so forth. Now, so the reason why we have to have 2 types of charges is because we got 2 types of forces. For gravity, it's only ever attractive, but for electric charges, you can have both attractive and repulsive. So let's say that I take this charge and I turn it positive by making that a positive charge. Now these 2 charges, instead of attracting towards one another, they will repel one another. And this would also work if both of these charges were negative. They would repel one another. So that's the way that charges operate. If the charges have the same sign, they repel. If the charges have opposite signs, they attract. So now we started talking about, so that gives you sort of the basic idea. And notice that there was remember with gravity, there was such a thing as a gravitational potential energy. And that was because, there was a force between the masses that were involved. The gravitational potential energy between my phone here and the ground has to do with the separation between my phone and the surface of the earth. It's how far away they are, and that sort of stuff. So there was a gravitational potential energy there. There's something similar here between these charges as well. There's an electrical potential energy that has to do with the 2 charges. And that actually, this idea of work and energy and stuff like that, actually explains the idea of voltage and what voltage means. The voltage has to do with putting in a certain amount of electrical potential energy because of the separation of charges. So when you have a battery, so I'll kind of draw, this won't be the best battery in the world, but I'm going to draw like a double A battery. So that's not the straightest line, that's even worse. But imagine that I'm a better drawer. Okay, alright, so there I've got that's supposed to be a cylinder, and then there's, on the top of these things, there's like a little nodule. And this is actually the positive terminal of the battery, and the bottom of the battery casing, way down the bottom, there's a little spot. There's a little spot where you can, a little metal spot on the bottom of the battery that's negative. Now here's what happens with a battery. There's a chemical reaction that goes on in the battery that supplies electric charge to the positive and negative terminals. And by separating those charges using the chemical reaction, a certain amount of electrical potential energy is stored in the battery. And when I connect this battery to some wires, which might go through, I'm going to make a light bulb here. There we go. That'll look like a light bulb in just a second. That's supposed to be the filament of the light bulb, and then here's the glass of the bulb or something like that. If I connect the positive terminal of the battery to the ends of a light bulb, and then connect to one end of the light bulb, and the other end of the light bulb gets connected to the negative terminal of the battery, now I allow a path for the charges which are liberated and have electrical potential energy they will gain kinetic energy and flow through the light bulb from positive towards the negative terminal battery, and we call this current. And I'm going to indicate an arrow here which indicates the direction that the current flows. And the rate at which the current flows is the rate at which charge is flowing per unit time. So I, the amount of current that flows, is the amount of charge that flows through any one part of the wire per unit time, or through the light bulb or anything like that. Okay, so what you want to think about when you see a battery is that's a source of electrical potential energy that we call, electrical potential energy and voltage aren't the exact same thing, but the voltage does depend on the electrical potential energy that is supplied by the chemical reaction that the battery is performing, and it liberates charge to move. Then it separates the positive and negative charges in the atoms inside of the battery. It separates them out and lets the positive charges and negative charges move through the circuit. Okay, so that's sort of some of the background that I wanted to give you about how electrical circuits really kind of work and why a battery works and what it does. It's a source of electrical potential energy that gives rise to something that we call voltage and so forth. So are there any questions on this? If there are no questions on this from the group in chat, just say no questions at this time or something like that. But if you do have something that you want to see, like how circuits work, or maybe the idea of resistance that we eventually talk about in our lectures this week, or electrical power, anything you want to know, just pop it in the chat. Don't wait for me to get to it necessarily, because who knows, I might not get to it. Depends. If you want to see something, ask something specific. Okay, so okay, cool. So no questions for the moment. All right. So here's the dealio with what resistance means. So what I'm going to do is, there's an analogy in the book that actually works out pretty well. It talks about how the flow of charge is a lot like the flow of water in a pipe. And in that case, if you want to make the analogy to how water would circulate in a pipe, then the voltage source is kind of like the pressure produced by a pump. So a battery is kind of like a pump, but it's a pump for charge rather than a pump for water. The flow rate that would happen of the water in the pipe, like gallons per minute or something like that, that flow through a particular section of pipe or something, that's like the current, except we measure the charge per unit time instead of the gallons per unit time, the volume per unit time. And then resistance represents kind of like friction or something like that. Basically, the rate at which, in a pipe anyway, the rate at which water can flow through a pipe is determined by the amount of choke points there are. The more choke points there are in a pipe, that's the limiter. So even if I have a huge pipe that's super wide and can accommodate a ton of water going through it, if later on in the pipe there's this really, really tiny narrow spot in the pipe, then that narrow spot in the pipe is the part that's going to limit the flow. And the whole circuit, the whole, circulating pipe system of water is limited by that one spot where the current is the smallest. So the current is the same throughout the whole thing. And it is determined sort of by that weakest link, that most restrictive choke point. And the same thing is true in an electrical circuit. So if I have a voltage source here, and these wires are really good electrical conductors, they're made out of metal, so charge flows through them like mad, really, really easily. But then they hit this light bulb where there's a material that's not very electrically conductive and charge doesn't flow through it very easily. Then this light bulb would be what limits the amount of current in the whole circuit. So the charge doesn't flow really fast here and then slow down and then speed back up here. It can only flow as fast as this element of the circuit, the light bulb, would let it. And this light bulb is it's said to have, then, in electrical terms, a large electrical resistance, which we characterize by R. Capital R is our symbol that we use for electrical resistance. So it turns out that there is a direct relationship between the current, the resistance, and the voltage. It's called Ohm's law. And it says the voltage in volts is going to be equal to the current times the resistance. And you will notice that this relationship, if you rearrange it, and this is a cause-effect relationship just like F equals MA was and all that sort of stuff. It's a cause-effect relationship. And this implies that if I wanted to solve for the current is equal to the voltage divided by the resistance. Okay, so notice what this relationship tells us. It says if I have a given amount of voltage here, which is sort of like a given amount of fluid or water pressure, then the more pressure I have, the more current I have. The more voltage there is in the battery here, the greater electrical potential energy is supplied to the charges to get them to move, the more current that I'm going to get. But notice that it is limited by the amount of resistance in the circuit. The greater the resistance there is in the circuit, the smaller the current there will be for a given voltage. So if I have a 1.5 volt battery here, and I have a big, huge old resistance here, then I'm not going to get very much current. So the not very much charge per unit time will flow. Okay. So now let's talk a little bit about the units. The units of charge, those have units called coulombs. It's named after the person who came up with the rule, the formula for the electric force. So just like, the Newton was the unit of force because Isaac Newton came up with it, with the basic ideas. Coulomb came up with the force law, the formula, which we didn't talk about. It's chapter 12 material. We talked about a little bit, but we didn't actually give the formula. But Coulomb came up with the formula for the force between two charges. So we name the unit of the charge the Coulomb, abbreviated capital C. Now, at the same time that Coulomb was doing his work in charge, a guy in France called Ampere was working on the idea of current. They didn't know that they were necessarily the same thing. So they named the unit of current after ampere, which you may have heard of the ampere before, or maybe you're more familiar with the sort of the abbreviation that we use for it, the amp. It's not really the abbreviation, it's really just the nickname for the ampere. So the unit of, so if I look at the basic units of the current, it's charge, which would be, so I'm going to say what units this is in. This would be in coulombs, and that's the metric unit of charge. And then I've got the time here, the metric unit that we use in the MKS system is the second. This then, the unit of the ampere then is the same as a coulomb per second, which we abbreviate A, or the amp, or and I'm putting this in parentheses. Or if you want to use the full name, it's the ampere, abbreviated capital A. So an ampere is a coulomb per second. Now, the volt is, the volt actually has units of a joule per coulomb. Now remember, joule is the unit of energy. So this is the electrical potential energy per unit coulomb that is given to every charge by the battery, for instance. Okay? So the volt has units of joules per coulomb. So V, and we abbreviate it, the joule per coulomb is the volt, named after Nikolai Volta, who basically built the first battery ever. the unit of resistance, so I'll pull that out here, the unit of resistance, just to give you an idea also, this expression here, V equals I times R, is known as Ohm's law. Okay, so this is Ohm's law right here. This is Ohm's law. Let me erase my circuit here so I have a little bit more space to work with. Don't need the circuit at this moment. This expression here, I'm going to use a double arrow to say we're naming this. This is Ohm's law. Named after Ohm, who was the first one who came up with it. Alright, so that's Ohm's law. Now, the unit of resistance then is the ohm, they called it. Now, here's where things get a little bit funky with the abbreviations. The volt is that's the abbreviation for that is V. The coulomb, capital C. The ampere, capital A. Ohm, you can't really do that with, because normally we would abbreviate ohm, the ohm, as capital O. Now, you probably can sense what the problem is with using capital O as your abbreviation for a unit. If I was to say this resistor is 1 ohm, let's say the resistor is 5 ohms. Okay, so if I was going to say that the resistance of this resistor here, say R is 5 ohms. Okay? And I would use O as the capital O. Yep. What's that look like? It looks like 50 rather than 5 ohms. You can't really use capital O because it looks too much like a 0. So, we don't use capital O. We go to the Greek letters and we use capital Omega, the Greek letter for O. So that's what this symbol looks like. It looks sort of like a stylized horseshoe. So if I wanted to say 5 ohms, I use capital Omega as the symbol for the ohm, which has the units of a volt per amp. Okay. So that's what's going on there. So that sort of gives you all the symbols and the units that are associated with them along. Now, there is a little bit of potential confusion here, that the voltage, the symbol we use is a capital V, and the abbreviation for the unit of volt is also capital V. Hopefully that's not particularly confusing, that you will be able to distinguish those at this stage. But it is a little bit, it can be a little bit confusing. Okay, so the symbol for voltage is capital V. The unit for the volt is also capital V. A little bit, potential for trouble, but hopefully not too bad. Okay, so now what I'm going to do is I'm going to introduce some ideas about circuits that we didn't really talk about necessarily in class yet, in the lecture notes and stuff like that. Specifically, what I'm going to talk about is how to draw a circuit diagram, because these end up being somewhat useful. But it's hard to just show in lecture notes and stuff like that. So that circuit that I drew before with the light bulb and stuff like that had resistance and stuff like that, I'm going to draw it using circuit diagram, circuit diagram symbols now. So the symbol for a battery is 2 parallel lines, but one of them is longer than the other. The longer side is the positive terminal battery, so I'll put plus there. And the shorter side of the battery is where the negative terminal of the battery is. Okay, a wire is just going to be a line. Wires have no resistance. It's assumed that they're such good electrical conductors that their resistance is 0. They would carry as much current as you want to put in them, infinite amount. The thing is, you always use wires to connect a device to it. So a device that has resistance is a squiggly line like this. So that is a resistor. And a light bulb is an example of a device that is a resistor. So this battery might have a voltage V between the terminals. In other words, from here to here, between here and here, there's a voltage difference of 1.5 volts, like a AA battery is 1.5 volts. And like a D cell battery is also 1.5 volts, but you could, like your car battery is a 12 volt system. The square alkaline batteries with the two terminals on the top, one of them's plus, one of them's minus. That's the one that you kind of got to snap things onto the top of. Those are 9 volt batteries. So different batteries can supply different voltages depending on the chemical reaction that they use. And they could supply different voltages depending on what you need. So that's why different types of devices use different batteries. So this symbol here is the resistor, and it has a resistance R to it. So a current then would flow in this circuit. So this basically is the same sort of circuit that I talked about earlier with the battery, where I drew a AA battery as a cylinder with a positive and a negative terminal on the top, and then I drew a light bulb with a filament in it. Well, that's there's some resistance in that, and there it is. There's a resistor. So this is the same circuit as before. Okay. Now, one thing that I want to note also is that you can actually have a whole bunch of different voltages that you can use in a system. So let's say, for instance, that you're talking about a flashlight. Okay. Now, you probably have seen a lot of the flashlights that you have. They use big D cells or C cells, or maybe you got a little flashlight or something like that, a little one, and maybe it's maybe it uses AA's or something like that. But usually you use more than one battery in them. Okay, and the reason for that is to up the voltage to supply more current to your light bulb so it's brighter. This is what you would actually do. You connect two batteries, one right after the other. You see how they're connected one right after? I have two batteries now connected one right after the other. And then I connect that to the light bulb. That's a terrible resistor, but you get the idea. And notice what happens here. The potential difference between this negative terminal and this positive terminal right here, 1.5 volts. So I'm going to do 1.5 volts between here and here. But then this one, there's another 1.5 volts between here and here. Another 1.5 volts of what we call in the business potential difference. So that means that the overall voltage between, say, right here at the bottom of this circuit to start with and the top right here, the difference is actually 3 volts. When you put two batteries, one right after another, that's called placing them in series with one another, because that's what a series is. A series is something where there's one right after the other. Stuff comes like the World Series is a series of games that are played. They're not played. They're played one right after the other. You can't play two games at once. But that's what goes on there. So these are two batteries in series. When you put two batteries in series, the voltages just add up. So if I had three 1.5 volt batteries put one right after the other, I'd have a 4.5 volt system. 1.5 plus 1.5 plus 1.5. And that's what happens in your flashlight usually. You put one battery in, and then you touch the negative terminal one, the positive terminal the other one, just like this connection here with this connecting wire. Okay, the positive terminal of this one touches the negative terminal there, and then the difference in voltage between this spot and this spot up here is 3 volts rather than 1.5. That gives you a little bit more juice, gives you a little bit more potential so that you can throw more current through the resistor. Okay. Does that make sense so far? I haven't seen any questions yet. Hopefully this is just all, super useful information to you all. But let me know if you have questions about how to calculate things too. That's or conceptual questions. Okay. So I'm going to continue while we go on here. So let's say that this situation here that I have, we'll look at sort of this top situation. Let's say that I have two light bulbs that I want to put in my circuit, one right after the other. So instead of a single light bulb with a resistance R, I put two light bulbs, one right after the other. That means I'm putting these two light bulbs in series. Okay. So let's say I have one light bulb which has resistance 1, and the second light bulb in the series has resistance 2. This is getting into the lecture material then for today. If I look at this now, I want to know, well, what could I do? How much total current is going to flow out of the battery through these two light bulbs? And the way to think about that is that if I combine these two resistors into one overall total equivalent resistance, so I'm going to call it Req, when the two resistors are in series, in other words, coming one right after the other, you just add them. So if this was 5 ohms, a 5 ohm resistor, and the resistance of the light bulb down here was, let's say, 7 ohms, then this circuit would act like it has a total resistance of 12 ohms, 5 ohms plus 7 ohms, and that would limit the amount of current that could be supplied by the battery even more than if I had just one 5 ohm resistor or one 7 ohm, because I have more resistance in my circuit overall. So that's how that works. When resistors are in series, one right after another, then I add the resistances to find out what the total resistance would be. Okay, so let's do a little bit of an example problem on that one. Let's say that the voltage here, I don't have much space to put it here, but I'm going to let's say the voltage of the battery is kind of what we've been talking about. Let's say it's a 1.5 volt battery. And if I had a meter in here that could determine how much current was flowing in the circuit, we want to know, well, how much current would that be through this system of two light bulbs. Okay, well, if I want to do that, I know from Ohm's law, I would use Ohm's law to do this. I would say V is equal to IR. I know that's true. And the total current that flows out of the battery would then be equal to the voltage of the battery divided by the resistance if I solve for the current. So solving for the current gives kind of that expression we had before, that the current is equal to the voltage divided by the total resistance of the circuit that we're talking about here. Okay, so this R down here is the equivalent resistance. It's not the resistance of any one resistor, it's the resistance of the circuit as a whole, and that'll tell us how much overall current flows out. So let's plug in our numbers here. We would get, in this case, if R1 was 5 ohms and R2 was 7 ohms, the equivalent resistance would be 12 ohms. Now that would have 1.5 volts divided by the resistance of 12 ohms. And that number that we get when we plug that in, oops, my calculator's down here, 1.5 divided by 12. This will give us the current in amps. So this is a relatively small current. It's 0.1, actually it's not too small, 1.25 amps of current, which is 125 milliamps of current. It's kind of like, the amp is kind of like the meter, the milliamp is kind of like the millimeter. So it'd be 125 milliamps, or 0.125 amps. So that's how you would find the current was that flows out of the battery. All right, so let's talk a little bit about what current does. There are biological effects to current. It turns out, and this is sort of a little bit of a sidelight, and I'm sort of pausing at this point to give this little bit of extra context for you so that you can ask questions in the chat. So please, again, ask questions in the chat if you have them at this stage. So my little sideline here is current affects the body. The electrical current flowing through the body affects all sorts of things. But one important thing to recognize is that, in a sense, there's a huge number of electrical circuits that exist in your body. Your nerves are essentially wires with resistance in them, and the electrical impulses that flow from your brain through your nerves actually make your muscles contract. So electrical impulses are what cause your muscles to contract. Now, if the current that flows through your, if there's a current that flows through your muscles that comes from outside the body, not from your brain, not from your nervous cell, but that the electrical current flows through your muscles because you touched a live wire or something like that, then what can happen is the electric current produced by that outside source can overwhelm the signal that your brain is sending to your muscles. This is why when you get electrical shock, you can have muscular spasms at the time. Now, some things that can happen then is if the current that is flowing through your muscles is bigger than the current that flows through the nerves from your brain, you could be grabbing onto a wire and you can find, I can't let go because it's causing my muscles to go into spasm and I cannot voluntarily let go of the wire. That's bad news. But that happens at around this level of amount of current. If you get about 50 to 100 milliamps, up to about 0.05 to about 0.10 amps of current flowing through your muscles, it can cause that sort of, you can feel a shock certainly at even lower currents, like 10 milliamps, 0.01, amps. But eventually you can get to a point where if too much current flows, then it actually can cause burns to your skin, to your muscles, and all that sort of stuff. And that happens at about 0.25 to 0.5 amps. So, and if you get up into multiple amperes, like 1 amp, 2 amp, 3 amps, anything in the 1 amp range is extremely dangerous current because in addition to overwhelming your nervous system and causing muscular contraction that is involuntary, which you cannot control, it's also at the same time causing severe burns. So this is why you need to be careful with electrical systems and stuff like that, especially ones that have extremely high voltages, because even though your body might have a significant amount of resistance to it, it could still produce high amounts of current, which could be damaging and harmful. So that's why we need to be careful with electrical systems. The human body is meant to have electrical currents in it, but not big ones. They should be, less than a tenth of an amp or something like that. Otherwise, trouble happens. So this is why you see signs at, where it says stuff like, warning or danger high voltage or something like that. It's really the current that matters because that's what is determining the size of the signal for your muscular contraction and determines how many, what sort of burns you might get. But it's the voltage which causes the current to happen. So that's why we don't have signs that say danger high current. It's the cause is the voltage in the first place. So that's why we say danger high voltage. Just to give you a sense about what is possible to happen and what sort of voltage that can happen. The voltage that comes out of your out of the wall sockets is about 120 volts. The voltage in the high tension wires that go down like 694, you can see them as you drive down 694 to Century. I know you haven't been there probably in a while, but those high tension wires there I think they're at 250,000 volts. So the voltages there are really high, and that's why they put them so high off the ground so that people don't, can stay away from them because people don't generally want to climb those big towers. That's why they make the towers so tall, is to keep folks away from those extremely high voltages. All right. So that's what happens when we're in series. So I haven't seen any questions yet, but let's talk about another style of connection. So what we talked about here was a series connection of two resistors. Another way of connecting resistors or light bulbs or whatever source, devices that are going to use electricity is to connect them in parallel. Now, I said in series, like the World Series, you have the games are played one right after the other in the same way that the resistors are wired one right after the other. In parallel, when a pair of games are played in parallel, it means that they're happening at the exact same time. So for instance, I can have you could play like during March Madness or something like that. Again, we didn't have it this year, but you've got games going on at the exact same time, and that means that they're happening in parallel. They're going on exactly the same time. So the same thing can happen here with resistors wired. So this, you'll notice, is a resistor that is wired in parallel with this other resistor. We're going to call this one R1, which I'm going to erase it so that so it's not confusing about which one is which here. This resistor here on the left is R1, so I'll put it here. And this resistor here on the right is R2. And again, we're going to use these same resistances. Let's say that this one is, let's say R1 is, again, just like in the top problem, it's 5 ohms. And I'm going to say R2 is, again, 7 ohms. Okay, so those are our resistors now. And now they're in parallel. The thing is, the rule for figuring out how much total resistance there is in this circuit is different. You don't just add these resistors. And here's the reason why. I talked about this really briefly in the lecture notes. It's easier to say it than it is to explain it in writing and stuff like that. At this spot right here, there's what we call a junction. A junction means that there is the opportunity for the current to split and flow two different ways. The more paths that there are, the bigger the current in this wire here can be that comes out of the battery, because there's multiple channels for the current, the charge, to flow. The more channels I have, the more opportunities there are for charge to flow, the bigger the total current can be that comes out of the battery, because here it splits and here it splits. There's multiple paths. It's like in the water example analogy that we made before. If I have only one really restricted place to go through, I'm not going to get very much water flow. I'm going to have relatively low current. But now imagine that instead of there being just one narrow pipe, let's say I opened up an opportunity where there was one narrow pipe and there was one wider pipe. Well, how much water then could flow total through that system of pipes is bigger, because I'm giving a larger opportunity. It's less restrictive because of more branches for water to flow through. The same thing happens here for electrical current and resistance. The more resistors are placed in parallel, the more paths there are for the electricity to flow, for the current to flow, and therefore what that means is that the overall resistance of the circuit, the equivalent resistance of this circuit, is lower by having more resistors in parallel. Okay, this is the way you calculate it, though. It uses what we call the reciprocal rule. The equivalent resistance is found. So that's supposed to be an E and a Q. Just man, I know that looks like an awesome blob, but maybe I can probably do better. Let's make it an E and a Q here, so I'll just have to make it a little bigger. Okay, so E, Q. Okay, so this is the equivalent resistance. If I have two resistors in parallel, it's the reciprocal rule. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. Okay. So, this one is a little bit harder to calculate. You got to use the reciprocal button. So let me show you. I'm going to pull up. Let's see if I can pull up my calculator here. There's my calculator app. All right. So I'm going to bring it over here so you can kind of see how I calculate things. Okay. So this is my scientific calculator. You might have one, something like this. Hopefully you're still got your calculators running around. But this is what I do. Okay. I said resistor number 1 is 5 ohms. Resistor number 2 is 7 ohms. So this is what I do. I say 5 ohms. I'm going to take the reciprocal of that. So there's the reciprocal button there. So that's 1 over 5 is 0.2. Plus, Okay, then I want the reciprocal of 7 ohms. So 7, and then I hit the 1 over button. Okay, 1 over 7 is 0.142857, so on and so forth. It's repeating, it turns out. Okay, so if I hit the equals button now, I will have the reciprocal of, the sum of the two reciprocals. So there we go. So that is the result that I get. So 1 over 5 plus 1 over 7 is 0.342857140, so on and so forth. Okay, that is the reciprocal of the equivalent resistance. Now to find the equivalent resistance, I just flip it over again. So I'm going to take the reciprocal of the result, and that gives me the answer. The equivalent resistance then is, we'll relook, basically 2.92 ohms. Okay, so I'll just put that here. 2.92 ohms. Notice that that is less than either 5 or 7. Having a 5 ohm resistor and a 7 ohm resistor in parallel, providing multiple branches for current to flow through, means that when you add these two together in parallel, you get a lower resistance than either one of the two individual resistances. Okay, does that make sense? I want to make sure that makes sense before we go. So remember that what my process was there. I take the reciprocal of 5, 1 over 5, plus 1 over 7, hit equals, and then take the reciprocal of that, because that flips what it was in the denominator goes in the numerator whenever I take a reciprocal. So that's how I calculate the equivalent resistance using a calculator. Okay, any questions on that? All right, so I'm pausing a little bit for questions, but I'm going to continue on this right now just to kind of, if I was then asking you, okay, I have these two batteries. Both of them are in series. And then, so they make a total voltage of 3 volts. How much current will flow out of these and then eventually get split between these two? How much total current flows out of the battery? Well, I would use V equals IR just like I used it before. So I'm going to make a little bit of space here so I can perform this calculation. V is equal to IR for this circuit now that I've drawn. Means that the total current that flows out of the battery will be equal to, I is equal to the voltage divided by the resistance, same expression that we have over here, except the voltage that I have is 3 volts. So notice I'm actually applying more voltage. Okay? But now I also have to divide by the equivalent resistance of these two resistors together. It's 2.92 ohms. And this is going to come out with a current in amperes, which we can perform our little calculation. Oops, I got rid of it, I guess. You could probably see. Okay, so it's 3 divided by 2.92 gives a current of 1.03 amps. Which is way bigger than this one. Now, it's double the voltage, but notice what happened here. Here I had 12 ohms of resistance when I put a 5 and a 7 ohm resistor in series. It's 12 ohms total. But when I put them in parallel, that resistance drops down to 2.92 ohms, which means more current can flow out of the battery. So even if this was a 1.5 volt battery, I would still get a really, really big, much larger current than when I put them in series. Putting them in series makes more restriction, more resistance. Putting them in parallel reduces the resistance by opening up, meaning the way that it's wired provides multiple paths for current to flow. Okay, so I'm going to pause, ask are there any questions now. You've been pretty quiet so far, but let me know what you're thinking. Hopefully it's been useful. Now eventually we are going to be talking about how these things work in real life. We've been, what's the sort of systems that you have in your house? I mean, everybody has electricity in their house, and you might be wondering, well, how are my circuits wired? How does my lamp get turned on? How does my computer operate? And all those sorts of things. And we'll eventually talk about those sorts of things. But basically, what happens is that there's another device that ends up in there called the switch. Very relatively simple device. It's just a device that says how much, whether current is allowed to flow or not. So I'll show you kind of what the circuit symbol is for a switch. It's like this. It's like I'm going to put a little node there and a little node here. So this looks like there's a gap, which would mean no current can flow. But then what you have here is like a little hinge with a thing that you could then imagine manipulating this thing, and you could touch this wire. You could bend this wire down at that hinge right there and touch the wire to that spot there, and then you complete the circuit. This whole thing then just becomes a wire. But this is a switch. It shows how you could turn it on by closing the switch here and closing the situation so that current can flow, or you can open up the switch and you can restrict and stop the flow of current. So that's what a switch looks like and how it operates. Now, one thing that you might notice is, so every device then in your house has a switch that allows it to be turned on and off. So let's say that it has a resistance to it. So I'm going to clear this out to kind of give you a sense about how devices work and stuff. Since I don't see any questions on this particular problem, I'm guessing that we're okay with it. So let's say that let's say that you have a voltage source. Oops, that's it. I have to be a little more careful with I lean back. It's always hard to draw with a mouse, right? So let's say I have a voltage source here. This is like the voltage that's in a plug or something like that. And let's say that you are going to wire all of the devices. Like, let's say you have a circuit at your house, and attached to that circuit there's a lamp and there's a television. Okay, so I'm going to represent those just as resistances. So let's say here's the lamp. Okay, your lamp has a switch. And then here's the resistance of the light bulb in the lamp. Okay, so this thing that I'm going to put in a dotted line, let's say this is the schematic representation of your lamp. Okay, so there in that box, that's your lamp. There's the bulb of the lamp, and there's the switch that you got to twist on your lamp to turn it on. Okay, and then over here, connected in the same circuit, is a television. Okay, so there's a switch to turn that on as well. And then there's the electronics inside of it, which we're going to represent as a resistance again. And then it completes the circuit. So you'll notice that whenever you plug something into the wall, there's a source, and then it's got a return. So there's, this is one end of the plug, and this is the other end of the plug actually. So this is going to be, again, this is your TV or whatever it is. Schematically, what's inside this box is your TV. Okay, so now notice what happens right here. Notice why this is not a good way to wire your house. Okay, let's say that you want to turn on your TV, but you don't want to turn on your lamp. Because maybe the lamp is right next to the TV, and you don't want to have the light shine on it because you want the TV to be nice and clear and bright. So here's your TV. And you close the switch. So you're like, I'm going to just make the connection there. So there it is. You close the switch. Okay. Does the TV turn on? No. Because you see the lamp here, its switch is off. It's in the way. No current can flow into the TV because no current's flowing through the lamp. Because current has to flow through the lamp to get to the TV, it doesn't work. So if you were to require, if all the circuits in your house, if every one of the plugs in your house was wired in series with one another, then you would have all sorts of trouble. All devices in the circuit would have to be on, or they would all be off. They have to all be on for it to work. So this is sort of a logic problem in some sense. So this is not how your circuits in your house are wired. That is not how they're wired. They're actually wired in parallel. Okay, so this is like your, the source from the, and then here's how it's actually wired. You've got a switch. Again, this is maybe like your lamp. Okay. And then this is your TV. Again, there's the switch. There is the resistance of all the electronics in your TV. And there you go. Now notice though, if I turn on the lamp, the TV could still remain off, but current will flow through the lamp, because even though there's kind of sort of a branch off to the TV part of the circuit, if the switch here is open, meaning that it doesn't allow current to flow through, it's in this position, just no current flows there. But there is a path for current to complete the circuit here, so the lamp will turn on while your TV remains off. Similarly, you could turn off your lamp and say, I just want the TV on. Okay, no problem. Then just do this. Okay, connect the, close the switch on the TV. The TV turns on. Current can't flow through here, but it can flow through here to make a perfect circuit. And so it'll, your TV will operate. So all the circuits in your house are actually wired in parallel. Okay, now, but here's what I want you to take away from this idea. It's a practical thing. What happens to the total current that's being supplied by your voltage source if you close both switches? So that what's happened to the equivalent resistance of this circuit? By closing both switches, both of these resistances now are being put in parallel with one another. The equivalent resistance goes down, and the current goes up. Okay, fine. But what if this isn't the only thing in your circuit? Let's say your whole living room is there. Let's say that you decided maybe it's a little bit chilly in your living room or something like that. Maybe this is in January or something like that, and you decide I'm going to plug in my space heater, and I've got my lamp, and I got my TV, and then I've got my Blu-ray player, and I got my super stereo system, surround sound system for my TV, and I turn them all on. So now I've got 4 things in parallel. What's happening then is the equivalent resistance for your circuit is going way, 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 way down. Every time you add a resistor in parallel, you lower the equivalent resistance even more. And that means more current's going to flow. That puts a lot of pressure on this wire right here. The more current flows through a wire, the warmer the wire gets. So, if you turn on a whole bunch of stuff here, there's the possibility that this wire could warm up so much that it starts a fire. We don't want that. You don't want to start a fire. So this is actually what happens. They put in a fuse or a circuit breaker in this wire right here. And what that does, a circuit breaker, for instance, and the fuse does the same thing, but let's talk about a circuit breaker. What a circuit breaker does, it has a sensor for how much current there's flowing through the wire that the circuit breaker is installed in. If it exceeds a certain limit that is set by the circuit breaker, like maybe it's 20 amps total is all you get. If you go bigger than 20 amps, the circuit breaker opens a switch. So it's normally closed, but it pops open. Okay, you hear a little click and it pops open. The switch gets opened up and everything turns off because this limits the amount of current that can flow through this wire, which feeds everything else. That's what a circuit breaker does. It maintains the safety in your circuit so that if you ask for tons and tons and tons of current because you got all these devices on, lowering the overall equivalent resistance of the circuit, if you ask for too much, it says, nope, can't give you that much current. You might burn down the house if you get it. So it stops it. Okay, so let's say that you did that. Let's say that, I turned on my space heater and my TV, my Blu-ray player, my super surround sound, and the lamp. I put them all on, and it lowered the equivalent resistance enough so that the total current flowing through the feed wire exceeds what the circuit breaker will allow. Okay, so what's the first thing you do? Okay, now, I'll just say what my first inclination is if I hadn't thought about this necessarily. I might have thought to myself, well, okay, I got to go turn the circuit breaker on. So I go downstairs. It's in my basement. It's right over there. Okay. The circuit breaker box is probably downstairs in the basement or something like that. And you go, okay, you look for the breaker that says that it's off. Okay, well I flip it back, so turn it back on, and what promptly happens again is you turn it on and all the lights come on for a second and then they go right back down. How come? Because you haven't changed the load. You need to turn something off first, right? So like, okay, I'm going to turn off my space heater because that probably draws a lot of current. It does. So I would open the switch, turn off my space heater, and then I could turn the circuit breaker back on and feed the circuit. And it's got a low enough equivalent resistance with the other one off that I don't draw too much current. So that's how circuit breakers work and why we have to wire things in parallel to make them work properly so I don't have to have everything on at once for anything to work. So I got to wire them in parallel. The downfall of parallel, though, is as we just discussed. The more stuff you put on in parallel, the lower the equivalent resistance of the circuit and the more dangerous the current will be in the feeding wire that feeds all of them. So that's why they install circuit breakers or fuses. If you have an old system, fuses are no longer up to electrical code, safety code. But that's sort of how it works. So hopefully this is giving you some sort of practical applications of what we're talking about here. Are there any questions on this? If you don't have any questions, just say no questions on this. It's so clear. You can even say this is so incredibly useful and enlightening. This is the most scintillating, awesome discussion of electricity that I've ever encountered. Maybe not, but there's something. So all your circuits are wired in parallel. All right. So, thanks, Josiah. I know it was very much prompted, but the other thing that we might talk about also, and eventually we'll discuss it next week, is there are some types of circuits that are wired in series. And this is an example of a set of devices wired in series. Is oftentimes, not all of them, some more expensive ones don't have it, but Christmas tree lights. So Christmas tree lights are wired in series. That way, when a light bulb in Christmas tree lights, at least the cheaper ones, when one light bulb burns out, you notice the whole string dies. So when a light bulb burns out, what's happening is the little filament that gets heated up because current is flowing through it, it gets so hot that it glows. Now they're designed to do that. That's what a light bulb does. It's designed to be robust enough to take that heat. The thing is, though, that eventually turning on and turning off that light bulb, eventually you get to the point where the filament wears out, gets too thin and too weak, and when you turn on the light bulb for the last time, the filament burns out right away. Burns out right then. It just pops and it just melts through, and now the filament represents an open circuit almost like a fuse would, or a circuit breaker. But it breaks the circuit, and since all the light bulbs are in series, if current can't flow through any one of the light bulbs, no current will flow through any of the light bulbs. And that's why you have the situation where if the light bulbs if you have one light bulb go out in a string of Christmas tree lights that are wired in series, the whole string goes out. Now, there are some more expensive ones where there's little ways to shunt the current through it after the circuit is broken by the burning of the bulb, and you can see which one is burned out and all the other ones are still on. Or you have other light bulb strings that are wired in parallel, but that's more expensive. They're more expensive. So if you want cheap Christmas tree lights, they're the ones that are wired in series. The more expensive ones with more wiring in them, more copper in them for wiring, those will be wired in parallel, and they won't break like that. They won't knock out the whole string if you're missing one light. All right. So hopefully that gives you a sense about how electricity works and why it works and what it does, and it gives you a sense of that. Now, the electrical code that I mentioned is basically it's a set of rules for the safety of all houses. So a trained electrician is supposed to certify any wiring, any new wiring that's done in a house, because they know the rules and they know how electricity works. The reason the electrical code has changed to say we use circuit breakers, not fuses, is let's discuss what a fuse is. So a fuse, you may have seen some fuses. They use fuses in some devices, but it's usually a breaker nowadays. But a fuse basically is, if I were to draw one, this is a little cylindrical fuse. It's a little, you got a sheath of metal on the ends, okay, like this, and then there's a little plastic surrounding it, and what it is there's a little wire that goes in here. It's a really thin wire, or it's actually a thick sort of wire, and then there's one extremely thin spot of wire that goes through, and then it widens out again. So this is like a piece of metal foil that gets really, really thin. Okay, and this connects the circuit. So if you're wiring your circuit, you have one of these fuses in here. Okay? And then current would flow into this fuse, flow through this thick metal foil that goes through here, and then, but to get to the other end of the circuit and the current to flow out, it would have to flow through this really thin area, which is really flimsy and heats up really easily. And what you do is you engineer the thickness of that film, that little metal foil in the middle, the thin part, and you use a material that has a known melting point, and you engineer it so that the thickness is just right, so that if the current that flows in through that foil exceeds 25 amps, that's a good, if it exceeds 25 amps, that little spot there gets so hot that it melts. And then the fuse is blown, they call it, and it breaks the circuit, and current stops flowing immediately. Okay? So that's what fuses do. That's how a fuse works. It's a really simple device. The thing is, these things are disposable then. Which means, if you blow a fuse, you've got to replace it with a new one that has the foil connected, obviously. It's not broken. Okay? Here's the problem. Fuses come, you might want different fuses for different applications. You might want a 20 amp fuse for one type of device or circuit. You might want 30 amps for another one. Other one you might want 25 amps. It depends on the wires that are connected to that particular circuit. Usually you're talking about 20 amps. Well, here's the thing. People are smart and people are dumb. There's both things. People are smart enough to recognize that replacing fuses is annoying, because you have to have a supply of them, because when your fuse blows, you want to pull out the old fuse, put a new one in, pop it in, no problem. The thing is, when you used to go to the hardware store and pick up fuses, it could be any old current rating. You could say, well, I need a 20 amp fuse. Now I want a 25 amp fuse. Now I want a 30 amp. I want a 40 amp fuse. The thing is, they all were the same size. They were just rated. They had different thicknesses for the foil in the middle. Okay, well, fine, that may be useful, but here's the deal about it. If you might say, well, my wire in my house says I'm supposed to only have a 20 amp fuse in here, but I'm annoyed because I keep asking for too much current, I'm just going to up my current to, I'm going to use a 25 amp fuse instead of 20. Here's the problem. The wires in the house are designed to be able to withstand 20 amps, no problem. 25 amps might be sketchy. But people would replace them because it would fit. I'll put a 25 amp fuse. 25 amp fuse is better, right? It's a bigger number. Except now, it's unsafe because they're using a fuse that is not consistent with what the design of the circuit was for the house. So you can start a fire by accident by saying, I'm going to let 25 amps go through, when actually 25 amps might start a fire. Or you could just, so people didn't understand what was going on electrically with fusing. They would say stuff like, well, it says 20 amps. They didn't realize that it was a limiter. They thought maybe it was, the fuse was something like the source. So 40 amp fuse is way better than a 20 amp fuse. I'm going to use a 40 amp fuse, which means turn on all your devices, no problem, right? The fuse won't blow. But the wire that it's protecting would start on fire, start a fire. Now so that's why they went away from fuses, because people had to replace them. Circuit breakers are designed, they're not replaceable thing, it's a switch. So people aren't liable to say, well, I'm going to replace my circuit breaker, which in principle you could. But if you change your circuit breaker, it's against the law to change the circuit breaker without getting a certified electrician to verify that it's right. So, and plus, it's a much more difficult task than just popping out a fuse and plugging in a new one. So circuit breakers are basically save people from making mistakes in the size of the fuses that they would use to replace the ones that burned out. Circuit breakers, you don't replace the fuses, you just flip the switch back on. But if there's still too much, but that circuit breaker is stuck, you'd actually have to cut the wires, pull out the breaker, replace it with another breaker of a different size. There's a lot of work to replacing a breaker if you're getting annoyed. But to legally do it, you would have to change the wiring in the house to do it. You have to pull out all the wires that are feeding all of your circuits as well, because that breaker is intended to match the wiring in your house. Okay, so hopefully it's sort of a sidelight, and hopefully it's sort of interesting, but I haven't received any questions today, which is pretty unusual. Hopefully this is useful. I've tried to add a little bit of context to what the lecture notes were talking about, and to give you some sort of real practical application of what's going on here. So hopefully it's been useful. Does anyone want to see, I haven't talked about electrical power yet, which is the subject of the lecture notes that are posted for Friday. You might have had a look at them already, but that's, if you haven't seen them already, that's fine. Do you want me to go over electrical power? If you do want me to talk about the idea of power, not power generation, but how we calculate the amount of power that's consumed by an object, go ahead and give me a thumbs up at the end. I know we're over an hour at this point, and I don't want to ramble on if you don't find it particularly useful or you don't want to see it just yet. But so if you do want to see me talk a little bit, 5 or 10 minutes more on electrical power, then give me a thumbs up, or please talk about power or something like that. Just let me know in the chat. Okay. So all right. So Mark and Josiah is saying, yep, let's see stuff on power. Okay. So let's talk about that. Let's talk about electrical power and how it's calculated. Avery says yes too. Okay, so folks are saying let's see stuff about electrical power. I'm sorry if I ramble a little bit on, but like I said, I'm trying to add context to things so that you have a sense about why this stuff is important and what the calculations we're doing are actually meaningful and useful in real life. It's not just nonsense physics that's just there for fun. It's actually useful. So remember what we talked about with voltages. We said that the voltage, the units of the volt is the joule per coulomb. Okay, so I'm going to say that the unit of the volt is the joule per coulomb. Joule is a unit of energy. So this is kind of like potential energy per unit charge that's flowing. Now, if I have, and then the current, I, is coulombs per second. The ampere is a coulomb of charge flow per second. So what's happening then, if I have a device that is connected to a battery of voltage V, and my device has some resistance in it, but it's a complete circuit so that current can flow, and this is a really simple circuit with no switches and no parallel or series connections. It's just one resistance, one voltage producing a single simple current. Then what's happening in this circuit is electrical charges, positive charges flow in this way, the way the current is, and then they run into the resistor. And what's actually happening inside of the resistor is the following. That electron, or that old positive charge that's moving through the resistor, it's bumping into stuff inside of the resistor, the atoms and stuff like that. It's like it's traveling through air, kind of like wind resistance or something like that. It's microscopic little collisions that the positive charges and the electrons and stuff like that are having inside of there. Now, when they do that, it actually makes the atoms in the resistor move a little bit faster. the charges are depositing the energy that they're receiving from the battery and depositing them into the resistance, which makes the resistor heat up. The question is, if they're depositing that energy, at what rate are they doing so? Well, the rate at which the rate at which work is being done on the resistor to heat it up is found from P is equal to I times V. The total power, which is the rate at which work is being done on the resistor, this is stuff from last chapter, can be calculated as I times V. The current that flows through the resistor times the voltage that is being applied to the resistor. Okay, all right. So that's how now notice how the units work out here. What are the units like? So I'm using this symbol here for the unit. So the current is the Coulomb, has units of Coulomb per second. That's an amp. All right, multiply that times the volt, which is a joule of energy per Coulomb of charge that is flowing. Notice what happens to the coulombs here. They cancel out, and I get joule in the numerator and second in the denominator. The unit of the joule per second. You remember what that one is? That's the watt. Capital W, the watt of power. So the rate at which power is being consumed by the resistor depends on its current and its voltage. Now, you can use V is equal to IR. Remember, this is Ohm's law. We can use V is equal to IR and plug that in here, and we can see, well, V is equal to IR. Then another way to calculate the power, a second formula, is I squared times R. It's I times R. Okay, so if you want to find out how much current is being dissipated in a resistor as heat, and this means like for a light bulb or for anything you want, but dissipated as heat. Maybe heat is actually the proper outcome. Like if you have a little electrical space heater, the power that it consumes is used to produce heat that then warms up your feet when you put them next to it. The way that you calculate how much power it consumes is say, well, how much current is flowing through it, square that current in amps, and then multiply by the resistance of the heating coil that the electricity is flowing through. And that will tell you the power in watts. Okay? The number of joules of energy per second that are being consumed by that device, in this case to make heat, if it's a heater. Okay, so that's how that works. The more current is consumed by a particular resistance, the more power is being consumed by the device, and the more power output there would be. It's the same thing actually for a light bulb. In a light bulb, the outcome of an incandescent light bulb with the filament in it, with like a tungsten filament in it, is light. Of secondary importance is the heat. You don't want the heat, but the heat is necessary to heat the filament up so that it glows and makes the light that you want. So this is actually a measure. So when you talk about light bulbs, like a 75 watt light bulb, what does that mean? It means that it is consuming 75 joules per second of energy from the power source that you're receiving from the power company, from the due to the voltage that they're supplying to you. So that's 75 joules per second are being consumed. Now there is an efficiency factor here. The light that comes out is not 75 watts. The total consumption is 75 watts. Only a relatively small percentage, like 20% or something like that, is actually going into light. The other part is going into heat and other losses that you're not actually using. You don't want that necessarily. But you get it as an outcome anyway. That's how much is being consumed. So a 60 watt light bulb consumes less power, and it means that because it's about the same efficiency, you get proportionally less light too. So that's why a 60 watt light bulb is dimmer than a 75 watt light bulb. And a 40 watt light bulb is dimmer than either of them. It's consuming 40 joules per second of energy to produce light and heat. You don't probably care about the heat, but you get the light as well. So that's sort of what works there. So that's what we mean by electrical power and how it is consumed. I will mention this as well then, that this process of producing light by an incandescent bulb, which is basically, it was Edison's invention way back when, we are now finally getting to the point we are not using that process anymore quite as often. The compact fluorescent bulbs use a completely different method. It doesn't heat up a filament that gets so hot that it glows and produces light. It uses a different process called fluorescence, obviously. The LED light bulbs, these are what are called light-emitting diode bulbs. They use a set of light-emitting diodes which are extremely efficient. They actually consume way less power to produce the same amount of light. They end up being like 70% efficient. So it means that you can consume way less power and still get the same amount of light. That's why on packages for these new LED bulbs, which are more expensive, they actually don't tell you the actual, they tell you it, but they like kind of hide it. They tell you, oh, this light bulb consumes 7.5 watts, but they usually put it in parentheses and put it in small letters. What they put in big letters is, it is actually just as bright as a replacement for a 75 watt light bulb. Oh, but it only consumes 7.5 watts. So it's actually more efficient. It's actually producing the same amount of light as that, but it's 10 times more efficient because because the process is different. And the process also does not put so much thermal stress on the device. So what that means is that when you turn on and off an incandescent bulb with a standard filament, every time you do that, it stresses the tiny little thin filament that's supposed to light up and glow. Eventually, that stress is enough to break it and it burns out. With an LED bulb, that process, there's not so much thermal stress because it's not using heat to produce the light in the first place. So it's more efficient and it lasts way longer. These things can last 10, 20 years. So that's the process of power generation or power use and stuff like that. So if I want to calculate the power that is consumed by a bulb in a standard resistance, you say how much resistance does it have, how much current goes through it. It's I squared R. You could also use P is equal to IV, but you have to know the voltage across the particular device as well. Either way is fine. Okay, are there any questions on that idea? And I think this covers all of the stuff that we were talking about in lecture and gives you a little bit of added context. I know it's been a little bit long, but I feel like I needed to add a little bit more context to make this a little bit more real world. Because it's not quite so mechanical and stuff like that as we've seen before. It's a little bit more, it's practical, but it seems maybe a little bit less mechanical and stuff like that. So if there are no questions, and I'm going to pause a little bit here too to let the questions come in as if they do come. If there are no further questions, then I'm going to end our stream today. Hopefully this was useful to folks. If you want to see an example problem or have any questions on the homework, now is the time to ask. And while I wait for any questions to roll in on this, I will say this. I have not graded the exams yet. I plan to do that a little bit later in the week. My other two classes that I'm teaching lectures on also have some things that had some stuff that was front loaded on the front end of this week, so I didn't get a chance to do those sorts of do the grading of your exam. But I will get your grades in. I think by the end of the day on Friday, I should have your exams graded and ready to roll there on that. So it looks like there are no questions from the group here. Hopefully this has been useful and informative to you. So next week, what my plan is for next week is to have our to finish out the rest of chapter 13. And then we will talk about, and then we'll begin a review for later in the week, because next week is the last week of the semester, and then the week after that we'll be having our final exam, our comprehensive final, which we'll still do. So yeah, that ought to work out as well. Then yeah, that should go there. So hopefully have a good rest of the week. Hope everyone is staying safe and healthy. And I will see you next week with more discussion on what the end of the semester looks like. But thanks again, and we'll talk to you later. Oh, question from Mark about the lab being posted. Oh, you're right. I haven't posted the lab. I will get the lab up. I will get the lab up later today so that you have that. I do have some meetings this afternoon, so maybe a little bit later in the day. Sorry about that. I didn't get the lab posted up yet for y'all. But I'll make sure that lab is up and posted by the end of the day today so that you'll have a chance to see and work on that. Also, the instructions will walk you through how to perform the lab as well. So my apologies on that. I missed the deadline on that one. Apologies for that. Okay, so I guess I'll end it there. But yes, that's on my to-do list by end of day today to have that to have the lab posted. So I guess I'll see you next week and have a great rest of your week and have a good weekend. Bye for now.